Hello all, welcome to the 64-bit edition of the SecurityTube Linux Assembly Expert course and certification. Now in this video, we will look at the stack. So really, what is the stack? Now stack is actually a temporary location available in program memory where we can go ahead and store data, variables, etc. while the program is running. Now, programs written in high-level languages such as C make extensive use of the stack. Now, from an assembly language perspective, stack operations are really quite simple and consist of either one of the following: a push, which is really going ahead and storing data on the stack, and a pop, which basically is removing data from the stack. Now this happens with one specific limitation. A stack is a LIFO or a last in first out, which means anything you put on the stack is going to be the first candidate which would be removed when you take data off the stack. The easiest way to visualize is really a stack of books, right? And if you wanted to take one book out, which is probably in the third position, and let's say you're not allowed to randomly pick books from the stack, then you would first have to remove the first two books on the top and then get to the third book. Now, the stack is a LIFO with one essentially very important aspect, which is the stack grows from high memory to low memory as far as x86-64 is concerned. Now let me show you what that means. So let's say we have high memory in here and low memory down there, and the top of the stack is always pointed by the RSP register, right? SP really stood for stack pointer. Now what I have done here is there are two pieces of data, both of them 8 bytes long, one consisting of the value 1122 up to 88 and the other consisting of the reverse of the previous one. Now, when we push new data on the stack using the push instruction, RSP is automatically updated and it now points to 8 bytes lower in memory versus where it was pointing before. Similarly, when we hit the pop instruction, the 8 bytes at the top of the stack pointed by RSP are removed and RSP is automatically incremented by 8 bytes so that it points higher up in memory. Now these are really the two operations. Let's look at an actual program with which we can understand this better. So you can download this file called stack.nasm. It's available just below the video. And I have put in very simple instructions. In the text section, first I move a large immediate value into RAX. Then I push RAX on the stack. What this means is push the value contained in RAX on the stack. After that, I push sample. Now if you remember, if I use the label name directly and sample is defined in here in the data section, then this really means basically the address referenced by sample, which is really the address of the sequence of 8 bytes beginning from AABB ending to 1122. Now in the next instruction I say push keyword sample, however inside brackets. What this really means is pick up 8 bytes, interpret as a keyword and push them on the stack. Now these are the push instructions where I have a push immediate, a push register, and then basically a pushing of an address and then pushing of data pointed to by that address. And after that I have 3 pop instructions to pop these data back to the registers R15, R14 and RBX. After that, we have the syscall which gracefully exits the program. Now, let's just go ahead and trace through this. So the first step is to assemble and link it. Now, of course, if we run this, it really doesn't make any difference because it just does what we've requested and exits. Now let's use our little friend GDB to load this up, and let's run GDB in our really friendly TUI mode, which we discussed before. Let's set disassembly flavor to Intel. Let's break at start. Let's run. Hit the breakpoint. Let me go ahead and lay out my assembly, and then let me lay out the registers, and then let me create a hook stop which can go ahead and allow us to examine the last four values on the stack. Right? Now let me actually do a step I. Now the first instruction really is to move this value inside RAX. Let's do that. There we go. Now if you notice, the top of the stack currently points basically to these values. At the very top you have the value 1 followed by something else. Now if you notice, the next instruction is push RAX, which is we will be pushing this value on the top of the stack. Two important things. The top of the stack would contain this value, and as the stack grows from high memory to low memory, the top of the stack will now point to a lower memory address than this one, in reality lower by 8 bytes. So let me hit an enter. And if you notice, the value in RAX was pushed to the top of the stack, and as you can clearly see, now we are much lower in memory as a data has been pushed on the stack. Now the next instruction basically pushes the address of the data which we had entered as sample. You can view that by saying x slash let's say 8xb, and then we can put in the value 0x6e4, and if you notice, we see our value AABBCCDDEFF1122, right? Now if we go ahead and try to interpret this as single 8-byte word, so single 8-byte value, sorry, as expected, because of the Edian-ness, this would go ahead and reverse, and we would really have the value 2211FF blah blah blah. Anyway, in the first statement we are just pushing the actual address on the stack, which is what you would see appear on the stack, and you can currently see the address is on the top of the stack, followed by the value of RAX which we had pushed inside. And now we are actually going to push the data pointed to by this address, and we are going to interpret that as a Q word, which really means this is what should now appear on the top of the stack. And as expected, after the instruction executes, this is really what we get on the top of the stack. Now after this is going to be 3 friendly pops. The first is in R15, and this would be the value which would go in R15. The next one would actually go in R14, and the final one in RBX, which we can clearly see in here, right? And after that we pretty much have the exit syscall, which ensures that the program exits normally. So this is really how one needs to visualize the stack and work with it. And the stack comes in really very handy when you want to use it as a temporary location to do stuff. When we get into shell coding, we'll see interesting things you can use the stack for to write shell code. That's all for this video. Please try this example out on your own. And if you're enjoying your time at Pentester Academy, please do recommend us to our friends and colleagues in the InfoSec community. We would really appreciate it and be thankful. Thank you.